Hello students, I hope you are doing well. So let us continue with the NCERT chapter 9 Hydrocarbons, in which today we will cover the theory part 6. There we will see the NCERT section 9.2.4. So this is our disclaimer. The learning objective of today's class is that you will be able to know much about this conformations of ethane. So we have already started with the conformation of ethane. In today's class, we will try to describe the same but in terms of some notations or in terms of some special projections, right? So today we'll study about those special projections. So we have basically two types of distinctive projections named as Newman and Sohers. Then after we will look on the conformation of cyclohexane. So this is a bonus topic for you. So basically, cyclohexane is kind of complicated molecule that does not exist in its real form or the expected form, rather than it exists in the chair form. So we will try to predict that chair form as well in today's class. Now, if I talk about the specific sections of the NCERT, then we will cover the NCERT section 9.2.4, conformations, and then after we will have a quick summary of today's class. So starting with the ethane conformation. So we need to have a 2D representation to represent the 3D molecular structure of your ethane molecule. Now this is a fundamental skill in chemistry as it helps us to visualize complex structure in a simplified manner. Another reason 2D representations are vital is that they visualize the relative positions of atom during rotations around the carbon-carbon bond. So this understanding is key when studying molecular dynamics and reactions. Okay, now let's move on to the type of projections in the chemistry. So these projections are method to represent the 3D structure of molecule in 2D. Understanding this will help us to interpret and draw molecular structure more accurately. So what are the type of projections? The first one is the Sohers projection. Okay, and the second one is the Newman projections. So basically, in today's class, our main focus would be on the representation of 3D molecular structure of any molecule with the help of a 2D representation, and those are of primarily two types. First is the Sohers projection and second is the Newman projection. Now starting with the Sohers projection of ethane. So we will try to specifically talk about ethane, and then you can apply this same logic to any other molecule. Here we have two images showing the Sohers projection of ethane. Notice how this projection gives us a clearer view of the molecule's 3D structure. The visual representation is essential for understanding how the atoms are arranged in space. Now, the view direction in a Sohers projection is from an oblique angle along the carbon-carbon double bond. So this perspective allows us to see the spatial arrangement between the atoms more clearly, which is important for predicting the molecule's behavior and reactions. First of all, in the Sohers projection, the carbon-carbon bond is depicted as slanted line. You can see it here in the diagram. This is the slanted line that is being written here. Now this slant represents the 3D angle between the atoms, helping us to visualize the molecule geometry and understanding its chemical properties. Now, from the viewer's perspective, if you see, the Sohers projection provides a clear view of the molecule structure. So this perspective is being given here. Now what can be said here? First of all, we have a front carbon. Now in the slanted line, the lower end is given to the front carbon. So here you can see that this is the front carbon that we have. Now this positioning help us differentiate between the two carbon and understand their roles in the molecule's structure and reactions. Then after, we have a back carbon here. You can see here that we have a back carbon and it is positioned at the upper end of the slanted line. So this distinction between the front carbon and the back carbon is important for visualizing the molecule's 3D structure and predicting its chemical behavior. So this is the first way to describe the ethane structure in a 2D way for Sauer's projection. I hope you are getting the point. Now here we have two structures. One is for the eclipsed and the second is for the staggered. If you consider it for the eclipsed one, then along this slanted line, both hydrogens are going upward. You can see it clearly that this hydrogen and this hydrogen is going upward. Whereas if you move on to the staggered conformation, we have a upward hydrogen and then we have a downward hydrogen. So these are the two possible projections, I would say two possible conformations of your ethane molecule shown with the help of Sauer's projection. Now moving on to the Newman projection of ethane. Again, if you see, we have a different view here. What is the different view? Now we are looking from the forward side. We are looking from the carbon side rather than looking at an angle, so that we are getting a slanted line. In case of Sauer's projection, we are looking from the front carbon such that the back carbon is hidden. Okay, so you can think of it in a way. Suppose you are seeing a queue or waiting for a bus. If you see the first person by standing right in front of him, then you won't see the person standing behind him. Okay, considering that all of them are the same physical structure, then you will only be able to see the first person, because other people will be confronted at the back side. Similar to that, if you have two carbon, if you look from the front side, you will be only able to see the front carbon. Now you can say that we are looking at the molecule in a head-on-head fashion along the CC bond. This head-on-head view is crucial because it allows us to see how the atoms are arranged around the bond. What about the CC bond? So in this projection, the CC bond is not visible. So there in the Sauer's projection, we have a slanted line to represent the CC bond. Here we don't have it because we are seeing it from the front side. Now what is the perspective from the viewer? So the front carbon atom is represented by a dot. So this simplification helps us easily identify which carbon is closer to us in the projection. So you can see here in the diagram that we have a dot here in the middle showing that the first carbon or the front carbon. Next, then you are seeing a big circle, right? You are seeing a big circle behind that dot, and that is representing your back carbon. So these are the representations of the two carbon, and now we are seeing from the head-on-head way. What is the advantage of this Newman projection? So the most important advantage is that it helps us to compare the angle in a much more efficient way. Like if you see the eclipsed and staggered structure, you can quickly see that there is an angle difference in the previous configuration of eclipsed and in the next configuration of staggered. Here it is shown by this double-headed arrow, right? So this is the angle by which the back carbon has been rotated so that the hydrogen is moved from being upside by slanted right side. Okay, so this is the most important, I would say the most good outcome of this Newman projection. Now moving on further. So that thing which we are talking about is the angle is called as the dihedral angle. So this has a special name. It is the angle between the two bonds on adjacent carbon atoms in a molecule. How it is measured? It's very simple. Imagine looking at the CC bond in the Newman projection way. So this perspective allows us to see how the groups attached to the front carbon and back carbon are oriented relative to each other. Now measure the angle between a group on the front carbon and a group on the back carbon. So that will help you to get the dihedral angle. You can see it here. So initially we have this carbon represented by a big circle, and the hydrogen attached to it is shown here on the upside. whereas the front carbon is shown by a dot in the middle, and here also the hydrogen is going upside. Now you are moving the, or you can say you are rotating the backside carbon, and therefore you are moving it by an angle of 60 degree onto the clockwise side. Okay, and that rotation is approximately equals to 60 degrees, right? Now your front carbon's carbon hydrogen bond and your back carbon hydrogen bond is there at an angle of 60 degree. You can compare each and every carbon hydrogen bond, each and every will have an 60 degree angle in case of staggered conformation. Now this angle that you are seeing between the two adjacent bond is named as dihedral angle. So this is the most important part and you should remember this. Again, I am repeating it. In case of eclipsed and staggered conformation, the difference between the bond angle is 60 degree. The difference between the dihedral bond angle is 60 degree, and you can see it clearly in this eclipsed and staggered projections of the Sawhorse way. Okay, sorry, the Newman way. Now, the first case, the angle is taken as 0 because they are aligned in a single line. But as you move the bond right hand side, or you can say if you rotate the carbon right hand side by 60 degree, then in that case your ethane will have a dihedral angle of 60 degrees. Now we will talk about the relative stability of ethane conformation. We have already talked about this with the help of staggered, eclipsed and skew conformations, but we will try to dealt it within detail. Here we have a diagram representing the different conformations of carbon. So basically this is called as an energy profile, where your energy is being varied with respect to the angle of rotation or with respect to the dihedral angle, right? Notice how the carbon are positioned in relation to each other. So this visual help us to understand the energy changes that occur during the rotation. So what you can see is in this rotation profile. So first of all, the graph shows an sinusoidal energy pattern with a 60-degree periodicity. Means after every 60 degree, you will see a similar kind of pattern. You can start from the first conformation and just look at the colored carbon. Okay, so we are rotating the front carbon basically, not the back carbon. If you rotate it by 60 degree, then it will go down in energy. Then if you rotate it further, then it goes up in energy. Means after every 60 degree, there is a periodic repetition. Got it? Now each full rotation includes 3 points of high and low energies. You can see here. So we started with the red carbon pointing upward, and after 3 highs and 3 lows, your red carbon is again oriented in the upward direction. So to make a complete rotation by moving 60 degrees, you have to go through 3 lower energies and 3 higher energies. Now let us talk about these energies. So starting with the first one. So what you can see, what is the initial phase of the molecule? So the first phase is the eclipsed conformation. Okay, so from where we have started it. Now it is the least stable conformation because you can see it also in the rotation profile that whenever the molecule is under the eclipsed conformation, it has the highest energy in case of ethane. Next, this thing is represented by the energy maxima, and it is occurring at an angle of 0 degree, then at 120 degree, means if you rotate it by 60 degree and then again 60 degree. Okay, so after 120 degrees rotation, you get a eclipsed conformation. So in that way, you will get it again at 240 degrees and again at 360 degrees. So these are the 3 maximas that you are observing after 0 degree. And this is representing your eclipsed conformation. Now let us talk about the second one, which is the staggered conformation. Here, it is the most stable conformation if you see that it is present in the minima side. And it is occurring at 60 degree, 180 degree and 300 degree. Again, it is getting, means you can say that every staggered conformation is being gotten by an angle rotation of 120 degrees. Now, why is this instability occurring in case of eclipsed and not in the case of staggered? So I think we have talked a lot about this in the previous class, where we saw that in the case of eclipsed conformation, we have an extra instability factor, which is the torsional strain. Now, this thing is not seen in case of staggered conformation in case of ethane. Of course, your steric strain is absent in both eclipsed and staggered conformations, that is for sure. You can also see one very important thing, that your eclipsed conformation and staggered conformation of ethane are differentiated by an angle of 12 point, not an angle, by an energy of 12.5 kilojoule per mole. Means the staggered conformation is stabilized by 12.5 kilojoule per mole of energy. Then after, what is the last conformation that we should know? It is the skew conformation, right? So we'll talk about it in the upcoming slide. Before that, let us mention the energy differences. Now, it is very clear that your energy difference between your eclipsed and staggered conformation is 12.5 kilojoule per mole, right? This is your energy barrier basically. So basically, if you want to convert your eclipsed conformation to staggered conformation, you have to provide at least 12.5 kilojoule of energy for per mole of the ethane molecule, right? Now, ethane can exist in both eclipsed and staggered form if you are considering them at the room temperature, because room temperature has enough thermal energy for their rotation. But still, your eclipsed conformation is the predominant one due to stabilization. Okay, so we have two factors for stabilization in case of ethane's staggered conformation. First is no strain is present there, and second is we have some electronic factor. We have seen this, that due to the overlap of sigma and sigma star orbital, an extra cause of stability is coming in case of ethane molecule in case of staggered conformation. Now moving on further, I said that we have left one kind of conformation. What is that? That is the intermediate or skew conformation, means the conformations that you are getting between the eclipsed and the staggered one. So basically, this is the top one representing the eclipsed and the bottom one is representing the staggered. But still, we have some conformations in the middle also. There should be a name for that, and that name is skew conformation. Now, it obviously it exists between the staggered and eclipsed conformation. Then, what is the energy expectation from the staggered conformation? Of course, since its energy is lying between the eclipsed and the staggered form, so you can say that it is more stable than eclipsed and less stable than the staggered form, right? Now, how can you just see it? So, if you are at a place where your angle of rotation is closer to your eclipsed conformation, then the skew conformation that you are getting will be thus less stable one, right? But if your angle of rotation is closer to the staggered conformation, then you will get a conformation that is more stable, right? So you can see here in the diagram as well. Suppose we are taking this instant, suppose this dot, suppose, then in that case your conformation will be closer to the staggered conformation and hence it will be more stable. Now, in place of that, if you take a higher point, or you can say if you are taking an angle which is closer to the eclipsed conformation, in that case you will see that the conformation is less stable as it is closer to the eclipsed conformation. Now, moving on further, we have talked about the eclipsed and staggered conformation. Then we also talked about the two kinds of projection, which is Sohor's and Newman. Then the second important part I would say is the conformation of cyclohexane. Now, what is so special about this cyclohexane? So, although cyclohexane is often drawn as a flat hexagon, but still it is not a planar molecule. Instead of that, it adopts a three-dimensional shape. So, this is crucial because the three-dimensional structure affects its chemical properties and interactions. How? Let's see. So basically here we have an image to illustrate the 3D structure of cyclohexane. Notice how it bends and twists, which is a key characteristics of its conformation. Visualizing this help us to understand the spatial arrangement. Now, the cyclohexane is adopting various conformation. If you see here, it has a chair conformation, it is a boat conformation, it is a twist conformation, twist boat conformation, half chair conformation. Now, all of these conformations that you are seeing for cyclohexane are merely the outcome of bends that your flat cyclohexane has undergone, right? Now, where it is bending, so basically it is rotating around the CC single bond, and that is allowed, you know it for sure, that due to the symmetrical nature of the sigma bond, alone sigma bond, it is possible to rotate the CC bond. Then this rotation leads to different 3D arrangement called as conformations, and such a conformation is there for your cyclohexane, which is named as chair form. We have another conformations also like board form, half chair form, and the twist board form. Now, understanding these shapes are important to explain its reactivity and stability as well. So we'll see how we are saying that we have a much more stable conformation of cyclohexane rather than the planar hexagonal one. So what is this problem? What is the problem with this flat cyclohexane structure? First, let us talk about the bond angle strain. So the first type of strain that we are encountering is the bond angle strain. In a flat cyclohexane, the bond angles are forced to be 120 degrees, which is not ideal for a molecule. So basically, if you see here, then to make a hexagon, a perfect hexagon, your C bond C should have a bond angle of 120 degrees. But you know that all the carbons that you are seeing in case of your normal cyclohexane is containing an sp3 character. Now an sp3 hybridized carbon is more prompted towards your 109.5 degrees rather than 120 degrees. So this is the first kind of strain, and it is named as bond angle strain, and it is coming due to the enforcement of your planar cyclohexane structure to 120 degrees rather than the ideal 109.5 degrees. Next, now this leads to an angle strain and deviation from the ideal bond angle. Now, what about the torsional strain? Is there any torsional strain present here? Yes, in flat cyclohexagon, adjacent carbon hydrogen bonds are eclipsed. You can see here that we have this hydrogen carbon bond eclipsed with this carbon hydrogen bond. So this creates a torsional strain in the planar cyclohexane structure. Then this repulsion increases the energy of the molecule, of course, and therefore contributing to overall instability of the flat cyclohexane structure. Now, to reduce all these strains, what will happen? The cyclohexane adopts a non-planar puckered structure. So this allows the molecule to relieve both bond angle and the torsional strain, achieving a more stable conformation. Now let's talk about this special kind of conformation known as chair conformation of cyclohexane. So this is basically a 3D shape which is adopted by the cyclohexane to minimize all types of strain. So this helps the molecule to be more stable. This is very important for understanding the reactions of cyclohexane as well. So this is basically happening with your cyclohexane molecule. It is bending like a chair. If you are seeing the molecule, we have a chair here. So this is the basic backbone of your cyclohexane molecule. Next, this is named as chair because it looks like a folded recliner chair. After that, it is the most stable conformation of cyclohexane. So we have seen various type of conformations for cyclohexane. We have the chair form, we have the half chair form, we have the board form, then we have different form. Out of these forms, the chair form is the most stable one. Next, what is the key structural feature of this chair form? So we will talk about this chair form in a deeper way. So first of all, they contain 6 carbon atoms arranged in a zigzag pattern rather than the non-planar shape. So this is the first one. After that, each carbon is bonded to one axial hydrogen, which is moving up or down basically. So it is represented by red color. Then next we have equatorial hydrogen that extends sideways. Okay, then rather than going up and down strictly, it is going in a sideways fashion. You can see here the blue colored hydrogens are your equatorial. Next we talk about the angle strain. So there is no angle strain present in the chair conformation of the cyclohexane, because all the angles are close to the ideal angle of sp3 hybridization, which is 109.5 degrees. So here the bond angle, if you see it in the case of chair form, then it is approximately equals to 109.5 degrees, which is very ideal for the sp3 hybridized carbon. So this minimizes the bond angle strain, and hence increases the stability. Next, let us consider the torsional strain. So in the chair conformation, there is no torsional strain because all the carbon hydrogen bonds are adjacent, right? So if you see here, if there is a hydrogen going upward, then the next two hydrogen are going in a sidewise fashion. So basically they are the equatorial one. So after each axial one, we have a equatorial one, and after each axial one, we have a equatorial one. So this is the beauty of your cyclohexane, so that it can stabilize it and free it from angle strain and torsional strain. Now, the staggered arrangement means that the bonds are as far apart as possible, minimizing repulsion. So this is similar to how people might sit in a room to avoid bumping into each other, ensuring comfort and stability. Next, finally, we can say that the chair form also avoids significant steric strain. The hydrogen are well spaced, meaning there is no crowding or clashes between the atoms. So this lack of steric hindrance further stabilizes the molecule. And we also know that the hydrogen are well spaced, so they don't do any steric crowding or clashes. So this is very obvious, and therefore we can trust them. Now let us talk about the Bort conformation of cyclohexane. So here is the Bort conformation of cyclohexane. What you can see here, when both ends of the carbon ring are bent in the upward fashion, then it results in a boat-like conformation. In the boat-like conformation, there are some problems, or there are some instability factor due to which it is less stable than the chair form. First of all, what about the angle strain? So of course, here we don't have any angle strain. Similar to the case of your chair form, the angle strain is absent here. It is because the bond angle is close to 109.5 degrees. Then after, we have a high torsional strain. So many eclipsed carbon hydrogen bonds are possible here, and that is resulting in your torsional strain, because this is eclipsing the energy increase. Okay. Next, what about the steric strain? So there is of course a repulsion between the two flagpole hydrogens. You can see here, it is represented here, that the two hydrogens are now very close to each other. Now they are that much close, so that they are capable of showing the steric strain, which was not seen in the previous case of hydrogen. In the case of chair form, right? Now open forms temporarily during the conformational change. So this conformation is of course adopted by the molecule, but for a shorter period of time. Now let us move on to the twist boat conformation of cyclohexane. So this is the representation for twist boat representation form. Okay, for the cyclohexane, here the bonds are slightly twisted to create a boat form. Okay, this half boat form, or the twist boat form, reduces some torsional strain as well as steric strain. So rather than clashing them head on head, now we have twisted it in a way so that hydrogen are not clashing with each other, reducing the torsional strain and the steric strain as well. Next, more stable than boat form because it is still less stable than the chair form. Next, we have the half chair conformation, which is the most stable one. So this is the no, not the most stable one. The chair conformation is the most stable one. So this is the half chair form. What you can notice here. So here, one corner of the lift of the ring is lifted up, while the rest is staying flat. You can see here that the 5 members of the carbon chain is in the same plane, whereas the one carbon is going upward. Now, it is representing a transition between the chair and twist board form. What would happen the next step? So this carbon having 120-degree angle or 120-degree bond strain will go down. So this is the next possible conformation of your cyclohexane from half chair form. After that, there is no actual resting state that exists. Okay. Now this is the highest energy conformation of all. So out of all the conformations that we just talked about, it is the one with the highest energy. Now let's talk about the stability of cyclohexane's conformation. So these are the pictorial representation of the energy profile diagram for the ethane molecule. So it is quite complicated. You don't need to draw this, but still you need to know them as well. So this is important. So what is the energy order? If you see it in the diagram, that the chair form is having the least energy. Okay, so it's the most stable one. Then we have the twist board form. Okay, then we have the boat, and then we have the half chair. Means your half chair is the least stable one. Then what about the stability order? So it will be opposite to that of energy. So chair will be have the highest energy. Sorry, the most stability. Then we have the twist board form. Then we have the board form, and lastly we have the half chair form. Now let us summarize our today's discussion. So we started with the ethane conformations, right? So it can be represented using the Sawhorse and Newman projection. Now two main conformations that are being represented by this Sawhorse and Newman are staggered and eclipsed, right? The energy difference between these two projections are, I would say the two conformations are 12.5 kilojoule per mole of energy. And the dihedral angle which is present between the staggered conformation and the eclipse conformation is 60 degrees, right? Then what are the cyclohexane conformations that we talked about? So it is not planar due to the angle and torsional strain, and 4 Mohn conformation in order of stability. What are those 4 main conformation? The first is the chair form. Then we have the twist board form. Then we have the board form. And lastly, we have the half chair form. So these are the 4 conformations of your cyclohexane which are adopted by twisting the planar cyclohexane structure. Okay. Now moving on with this cyclohexane conformation. So chair form is the most stable one, we know that. Then here the bond angle is close to 109.5 degrees and your angle's torsional strain is absent here. Got it? First of all, of course, they will contain the axial and equatorial hydrogen because we are talking about the cyclohexane. Then moving on to the twist board form, what about it? So here it is more stable than the board form because here we have some amount of angle strain. Then we have the board form. So it has a flagpole hydrogen interaction. So basically, due to the very close approach of two hydrogen, it shows a steric strain, which is known as flagpole hydrogen repulsion. It is compared to the higher torsional strain, and the last one is the half chair, which is the least stable one. So this least stable one is transitioning from the chair form and the twist board form. So whenever you see cyclohexane at room temperature, it is basically going from one conformation to another. It is going from twist board to half chair to chair and so on. So this goes on continuously. Now, this was all for today's class. Thank you for joining the session. I hope you enjoyed it.